Hello and welcome to a new video. This is for Algebra 1. We're in Unit 9, Graphing Quadratic Functions, Lesson 2. And so, Lesson 1, we first started talking about graphing quadratic functions and we just stuck with monomials, so just one term, and saw that putting a number in front of x squared maybe stretched our graph vertically or shrunk our graph vertically. And so today we're going to add to that by looking at the other things that we can do to graphs. So let's go ahead and take a look. First off, there's this idea in math as far as graphing goes, and this is specifically for functions. We have these functions that all kind of do similar things when you get down to moving them left or right or up or down or reflecting them or stretching them. It's just that the thing you're doing to them can be different. So for instance, quadratic equations involve having an x squared, right? And so that's different than having an absolute value equation, which instead of having an x squared should have absolute value bars. But if we do things to those functions, like add a number here or add a number there, they actually behave in the same way, which is really neat. So what we do is we have kind of this idea of parent graphs. And this is very similar to like if you're thinking about, parents and children and how they're related to each other. I mean, not exactly the same, obviously, but like we think of the parent graph of these different types of functions as this is what it looks like when I haven't done anything to it, when there's no extra numbers. It's just the simplest that function can be. So for us, with our quadratic equations, that would be just having y equals x squared. If we can memorize just what y equals x squared looks like, and then we memorize the rules for transformations, then we actually can graph any quadratic equation using these transformation rules. And I think it's really neat. I personally like it a lot. And this is something we'll build on in Algebra 2 and in pre-calculus with other functions as well. There's depending on what book you look at, there's like 12 basic functions or more, just kind of depends on what you want to define as a basic function. So let's start off by just remembering from last lesson what y equals x squared looks like. Because it's a pattern that I think is actually pretty easy to remember. Y equals x squared, we're just squaring our x values, so it's going to start at 0, 0. And remember, that's called our vertex. It's going to be our bottom point. Then here's how I like to think of it. From 0, 0, we go out 1 and up 1, because 1 squared is 1. Okay, and then back from our vertex, we're going to count again. So from our vertex, our next point is out 2 and up 4, because 2 squared is 4. And we could keep that pattern going if we wanted to and say, well, if I go out 3 each direction, then I should be going 3 squared up, which is 9. And if we can remember this pattern, then what we can do is we can use this as we move our graph around. Left, right, up, down. Slide to the left. Oh, well, that's your right. Slide to the left. So yeah, that's the idea there. So these transformation rules, we have 4 basic types of, well, actually, I guess 3 different types of transformations. We have shifts, which the fancier word for that in math is translation, that we're talking about moving left, right, up, or down. And so if all that's happening is a shift, which is what we're going to mainly be looking at today, then we're going to have that same pattern of out 1 and up 1, out 2, up 4. We have that same pattern because it keeps its shape if it's just being shifted. It just moves the location of each point based on where it's being shifted. So these next two are kind of the same in the same category of transformations, stretching and shrinking. And what stretching or shrinking does, or compression is another word for shrink, is it moves the graph's points either farther from the origin or closer to the origin. I actually probably should have said vertex, because if we've shifted around, then the vertex might not be at the origin anymore. Technically, we can stretch or shrink both vertically and or horizontally which is one of the things that makes all of this complicated. So we'll try to work our way into that a little bit. What we saw in 9.1 was we saw vertically stretching or shrinking, that whenever we times the x squared by a number in front, it either makes it go up faster or it makes it go up slower. So it brings the points closer to the vertex. And then we also saw a reflection in 9.1. Reflection is when you move the parent graph so that each point is the same distance away from the x or y axis. Typically, we reflect over the x-axis much more so than we reflect over the y-axis. And for parabolas, if we reflect over the y-axis, it actually, if it's centered on 0, 0, it looks the same. So we're just taking, if we reflect over the x-axis, we're taking the points and we're making them go face down instead of up. And so that's called a reflection. We're flipping the graph. So what we're going to do on each example is we're actually going to start off by graphing the parent graph, y equals x squared. I want to encourage you to have a different color pen or pencil handy so that you can see really easily which graph is which. And in fact, you might go through and just go ahead and graph y equals x squared over and over again here. Because on each of these, we're going to graph y equals x squared, and then we're going to graph something else with it, and then we're being asked to describe the transformation. So part of this is, in fact, to make sure you get enough practice thinking about how to graph y equals x squared. It starts at 0, 0. You go out 1 and up 1, both directions. You go out 2 and up 4, both directions. Here is y equals x squared. So I've given a table of values here that we can use. It's intended that you wouldn't need it necessarily for graphing y equals x squared, since we've already done that a decent amount. But it might be that it helps you to do the second graph here. So y equals x squared plus 1. And it may be that you don't have too hard of a time, thinking through and figuring out what this would do to the graph, and that's great. But if you do, here's the idea. We would take 0 squared, and then we would add 1 to it. So that's going to make this vertex point in the middle be 0, 1. At 1, we do 1 squared plus 1. Make sure you do the exponent first and then add. So that's 2. This is 2 squared plus 1, which is 5. Notice that, and I guess we should have made a table of values for the parent graph, so we had an easy thing to compare to. But each of these are up 1 from what the parent graph is. And that pattern would continue this way as well, that plugging in -1, you square it and you get +1, you add 1 and get 2. If we graph this, basically each of these points is just literally moved up 1 spot. They're still lined up. They're still lined up here, with our x values, but everything has been moved up 1 spot. And the farther up we go, the harder it is to make it look like there's a difference there. But that's the idea. So describing the transformation, this is a shift or a translation up of 1. And so you may notice we have a +1 here, and we shifted up 1, and that is absolutely a connection we should make. If you have x squared and you add something to it, then that's going to make it go up or down. Add would make it go up, subtract would make it go down. Well, let's take a look at another one. So we're going to graph our parent function, 0, 0, out 1, up 1, out 2, up 4, and then we're going to look at this. So, by the way, we have 2 basic approaches for graphing once we leave the very nice world of lines. And that is either we memorize the parent graph and transformation rules, or we use a table of values. If we're not allowed to use a calculator to graph it. And so that's basically what you at some point need to decide is, am I going to commit to learning these rules, or am I just going to sit and make a table of values every time? And both of those are fine options. I'd like for you to at least give the transformation thing a try because I think it's neat. But I'm just asking for a try. You may not end up liking it. So what's happening here in our equation is we've got this -2. Based on what I just said a second ago, can you predict what's going to happen to this graph? I hope so, but I don't know. So if you need to use a table of values, right, we'd do 0 squared minus 2, 1 squared minus 2, 2 squared minus 2. And I do want you to be a little cautious here about assuming that it's the same on the other side. We are going to end up with some that our vertex does get shifted left or right, and that's going to make a difference. But in this case, our vertex isn't being shifted left or right. We're actually shifting down 2 because of this -2. Okay, so each of these points goes down 2. And so if I knew that going into it, I would not actually need to make the table of values. I'd just say, here's where I know it normally is. Let me move each of these points down 2. All right, so there's our parent graph and our new graph, and our transformation is a shift down of 2. Notice I didn't say like shift up of -2, although you could argue that that would be correct. It just doesn't really quite give the information the same way we've moved it down to. Okay, so now let's look at something a little bit different. We've got an x plus 1 in parentheses and then a squared. So what's happening here that's different than our first example is that this +1 is affecting x before you're squaring it. And that makes actually a really big difference. It's actually weird to think about, at least for me in my head. I know what it does, but I don't know that I'm super good at thinking about why it does it. So let's go ahead and graph y equals x squared. Hopefully you're getting the hang of this pattern here. I start at 0, 0, out 1 and up 1, out 2 and up 4. Voila. Then let's use the table of values to figure out what's going to happen here with that +1 inside. So when I do 0, order of operations says do parentheses before exponents. So we need to do the 0 plus 1 and simplify that before we square. And if you are thinking, oh, this is like 0 squared plus 1 squared, technically works for this one, but that's not actually how you do it in general. You add inside the parentheses because you can, and then we square. So 0 plus 1 is 1, and then you square it and you get 1. And just by the way, if you're thinking that this is the same as x squared plus 1 squared, it's not. You would actually, now that we know how to multiply polynomials, we'd actually have to do x plus 1 times x plus 1. There's not actually a good reason for us to do that, though. I'm not saying to do that. I'm just saying this is not the same as just x squared plus 1, because that would imply that we're shifting up 1. That's not what's going to happen here. All right, let's do 1 plus 1 squared. So 1 plus 1 is 2. 2 squared is 4. And then let's do 2. 2 plus 1 squared. So 2 plus 1 is 3. 3 squared is 9. Now, we've been able to, up until now, just repeat the numbers up for this -1, -2. But if we notice here that 1, 4, and 9 is our pattern just shifted over, then that would imply that this is not going to be 4 when I plug in -1. Let's see what happens when I plug in -1. -1 plus 1 is 0. 0 squared is 0. Okay, so wait. That means that instead of us shifting up or down, we actually are shifting all of our points. Is this left or right? I feel like this is left, because at -1 we're at 0. Instead of at 0 we're being at 0. So this is where we may actually need to adjust our table of values. This is negative 1 squared, which is 1. Or maybe we can just use symmetry to help us. So we have 0, 1. We have negative 1, 0. We have 1, 4. I can graph 2, 9, or I can just leave it off because we didn't graph the 9 for our parent graph. Negative 2, 1. And so then based on symmetry around our vertex, which is at negative 1, 0, our next point over should be at negative 3, 4. We can plug that in if we're not sure. Negative 3 plus 1 squared. That'd be negative 2 squared, which is 4. So when I plug in negative 3, I get 4. So check this out. This has been shifted left 1. Now, you may be thinking, wait a second, that says plus 1. I happen to know that plus 1 means that we go in the positive direction, which would be to the right, not to the left. How does that work? So there's this thing that happens with functions that I like to call the super secret opposite society. And someone else explained this to me. This is not a K-Steve original idea, but I'm going to pretend like it is. So the super secret opposite society in math is basically that anything that's inside of parentheses in a function actually does the opposite of what it would do if it was outside of our parentheses. So the fact that plus 1 outside means to go up, which is the positive direction, what's happening inside the parentheses is actually going to do the opposite of what we think it is. So a plus 1 actually means we're going to go in the negative direction. The other thing happening here is that plus 1 is directly affecting the x, and so that's going to help us remember that it's a left or right instead of an up or down. So inside parentheses makes it go left or right, but it's the opposite sign, so it's shifted left 1. So then we can generalize that and maybe not have to make a table of values in the future by saying, okay, I know if it's in parentheses that I'm going to take the opposite because it's part of the super secret opposite society and make it move whichever direction that means. Let's do another one. So this one has x minus 3 in parentheses squared. So what's cool about this is if you're getting the hang of it, you might be like, okay, well, based on this last one, I know exactly what this is going to do. And that saves you from having to make a table of values. We always can make a table of values. That is the thing we should do if we can't think of what else to do to graph something. Oh, I missed it. But if we feel like we know what's happening here, okay, this minus 3 is part of the super secret opposite society. So negative for x is to the left, but we're going to do the opposite, and we're going to say this goes right. This is a shift right of 3. Okay, so we make a table of values, or we can just sit here and move these points over. 0, 0 would move over to 3, 0. 1, 1 would move over here. The other thing to do is to just move your vertex and then say, okay, well, I know the pattern from my vertex is out 1, up 1, and out 2, up 4. That's the other way to do it. And that would mean that we wouldn't actually have to draw our parent graph. We would just need to know, but we'd still know the pattern. We would just move the vertex over and then do the pattern from the vertex. Something about my second parabola looks funny. I apologize for that, but yeah, that's life. All right, so now let's put these two ideas together with y equals x plus 2 squared plus 3. So we have two things happening here, a plus 2 inside and a plus 3 outside. So to bring all of this back to like together and summarize it, the plus 2 on the inside is affecting x directly. So it's going to make it move left or right. We take the opposite. Instead of a plus 2 meaning right 2 inside, it means left 2 because of the super secret opposite society. So this is a shift left 2. The plus 3 on the outside is going to be a shift up or down, because what's happening is that we've already taking care of squaring our x and our plus 2. And so then it's going to take whatever we have and it's going to either add or subtract to it because it's outside. So since it's a plus 3, it's going to shift up 3. So I'm going to draw my parent graph because parent graphs are great. And then we're going to take each of these points and shift left 2 and up 3. So left 2, up 3, left 2, up 3, left 2, up 3, left 2, up 3, left 2, up 3. Again, I could have just shifted the vertex and then done the pattern from there. I don't know what my problem is with these second parabolas looking kind of funny. But that's the idea. We shifted left, we shifted up, and voila, we got it figured out. So 9.1, we explored the idea of stretching our graph vertically or shrinking it vertically and reflecting. Here we've talked about shifting it left, right, up, or down. And so next lesson, we will actually kind of combine these all together and talk about vertex form, which is the best form, and how that's going to help us with graphing quadratic equations as well. Thanks so much for watching. I hope that you enjoyed this video. Graphing can be something that's really daunting at first, so it's definitely, you want to do a lot of practice. If it's that you don't like how your graphs look because you don't feel like you're very artistic, I get that. I don't feel like I'm a very artistic person. And I'm definitely a selective perfectionist, so I get that. So you just have to do the best you can and accept that your graphs might not look perfect. So yeah, hope you like this video. Give me a thumbs up and subscribe if you haven't already, and I'll see you in the next video.